In this video, I'm going to do some examples of problems from section 9.2. Those are problems involving slope fields and what is called Euler's method for finding approximations when you have a differential equation. So I'll start with slope fields. We'll talk about, you'll have some notes from class, and this will just serve as a video to help support you in doing problems from section 9.2. So to create a slope field, I'll do an example here. Let's say we have the differential equation dy dx is equal to x squared. We'll start with that example. And let's say we want to make a slope field that includes the points from -2 to 2 on the x and the y-axis. So that seems like a pretty small range, but to do that, that's going to actually be 25 points. It's 5 by 5. And when you do this, we usually put little dots at all of the quote-unquote nice points. So there's a little -2 to 2, -2 to 2 window. Okay, so this slope field only depends, or this differential equation only depends on x values. So we could start, for example, with the origin. At the origin, this is the point 0, 0. Now, the point 0, 0, we're only interested in the x-coordinate. We take the x-coordinate and square it, and that gives us a slope of 0. So I'm going to sketch in here a little line segment that has a slope of 0. And then I'm going to move up here. This is the point 0, 1. Once again, the x-coordinate is all we really care about here. So the x-coordinate is 0, squared is 0. X-coordinate here is 0, squared, same here, 0, and 0. Okay, move over to here. All these points have x-coordinate 1. And when I square 1, I get 1 squared. So I'll sketch in a little line segment with a slope of 1. And since it only depends on the x-coordinate, and all these lines, or sorry, all these points along this vertical line, I'll have an x-coordinate of 1. They all have the same slope. And when I go over to x-coordinate of 2, 2 squared is 4. And I'll try to, you don't have to be perfect with your slopes here, but certainly want it to look steeper than 1, right? I'll try to sketch in some lines that have a slope of 4-ish. Okay, going over to the points that have an x-coordinate of -1. Well, -1 squared is +1, so I'll do my best to make them look the same. Of course, slopes of 1, it's just a little 45-degree angle, right? And then an x-coordinate of -2. -2 squared is 4 again. So I'll try to draw something that looks steeper. And there's our slope field. Now, what is a slope field? What are we looking at here? We're looking at a sort of a possibility of all the different functions that could go through this slope field, what their slopes would be, and basically we're looking at what solutions of this differential equation might look like. So for example, if we were asked to sketch one of the curves that started here, we would say, okay, if I'm started here, then my little slope line says I should go in this direction. But it doesn't just go in a straight line. You can see as we move this way, the slopes start to get less steep. They start to get less steep, and then maybe by the time they get over to here, they're going in this direction, and then they get less steep until when they cross the y-axis and they get more steep, and then even more steep again. So a curve that goes through there might look something like this. And what does that look like? Well, that looks like a cubic function, doesn't it? Well, it should, because, of course, the solution for this is an easy differential equation to solve. We just do that and then integrate both sides and get y equals x cubed over 3 plus c. So it's these cubic functions here with the plus c, and the plus c means, well, I could have started here, and then I would get one up here, and so on and so on. So slope field, notice that we were sort of sketching the slope field for x squared, but it didn't come out to be parabolas, right? Because these are the slopes. So the slope field for x squared looks like this family of curves. Right? Now that was one that was very easy to solve, but sometimes we get slope fields for differential equations that we can't solve because they're not separable. For example, x plus y. Now, no matter how hard we try with the techniques that we have, we can't separate that into y is on this side and x is on this side by factoring and dividing. So we can't do this, but we can still get a visual for what the solutions for this might look like by sketching the slope field. So I'll just make one the same size again, and we'll see what it looks like. If you're asked to do this on a test or quiz or on an AP test, they'll give you the little grid here. You don't have to make this yourself. And you only have to sketch in the points for as big as the grid is. And I don't think I've ever seen one on the AP test that was bigger than this, and that would be a big one. Because it's kind of time consuming, right? Alright, let's go through point by point. I'll start at the origin again. The coordinates at the origin are 0, 0. So 0 plus 0 is 0. So I sketch in my slope of 0. This is the point 0, 1. When I add those two coordinates together, x plus y, I get 1. This is the point 0, 2. Gives me a slope of 2. Here, this is the point 0, negative 1. That'll give me a slope of negative 1. And then this will give me a slope of negative 2. So that's what those slopes look like along the y-axis. This is the point 0, 1. That'll have a slope of 1. 1, 1. That'll have a slope of 2. I'll try to make it look the same as that 2 there. And this is 3, a little bit steeper. And then here, 0, negative 1. Oh, sorry, this is 1, negative 1. 1 plus negative 1 is 0. And then this is 1, negative 2. When I add those together, that's right there. Okay, and then moving over here, this is 0, 2. 1, 2, 2, 1, sorry. It's 2, 0. Same slope, but and this is 2, 1, so that would have a slope of 3. And then try to make that look a little steeper. I'd have a slope of 4 at 2, 2. And I have 2, negative 1. That would have a slope of 1. And then 2, negative 2. That would have a slope of 0. And I start to see some patterns here, right? They just go up 1 every time as you go up, and up 1 every time as you go over, right? Makes sense. So I'll sketch the rest of them in quickly here following that pattern. Those are all the zeros. And then here would have a slope of 1. That's 2 and negative 1. And these ones would have slopes of negative 1. Alright, that's negative 2, 1. And these ones have slopes of negative 2. These ones have slopes of negative 3. And negative 2 has a slope of negative 4. So whatever the solution curves for this look like, if we could actually solve for them, they look like curves that do this. They might come in, if I had to sketch one, might come in like this and start to bend up like so. And you can see that it looks like this line, what is that, the line y equals negative x minus 1. It looks like that's some kind of asymptote here. I'm going to get closer and closer to that. If I started down here, solution curve would go down like that. So it's some interesting family of curves. It's not just a matter of a plus c that moves it up or down, right? Because this one depends on both the x and the y. All right. Now, let's talk about Euler's method. This is a method for finding approximations. So if we started, for example, if we had the dy dx is equal to, we'll do the x plus y we did in the last one. And let's say we know that we have a curve that goes through the point, let's say negative 1, 1. And then we want to find an approximation using Euler's method for the point, let's say, I'm going to scratch that 4. Ooh, not a good eraser. Sorry about that. Yuck. Let's say approximation at x equals negative 0.5. I'm going to do a pretty detailed one here. You won't have to do one with this many steps typically, but I'll do one with lots of steps so you can see how that works. And then we have to decide how many steps we're going to take to get from negative 1 to negative 0.5. So I'll say with 5 equal steps. Right? So we're going to step from negative 1 to negative 0.9 to negative 0.8 to negative 0.7 to negative 0.6, and finally we'll get to negative 0.5. Basically what we're doing is we're doing 5 little tangent line approximations. And we're saying, like, since the slopes are constantly changing, we'll step just a little bit and then we'll reevaluate, find the new slope, and then step along that tangent line and then reevaluate what the slope is and then step along that slope, and so on and so on. Here's, I think, the best way to do that. We'll set up a little table. Here is my x-coordinate, my y-coordinate. Here is dy dx, which of course you can find by our formula right here, our differential equation. And then here's the key. Since, I'll write this off to the side, since dy dx is approximately equal to, at any point, delta y, delta x, especially if the delta x is sufficiently small, those two things should be approximately equal to each other. And it's like saying the slope of a tangent line is equal to the slope of a secant line with 2 points that are pretty close together. We know that that's true. Now multiplying this around a little bit, it tells me that the change in y should be approximately equal to the slope times the change in x. Right? So I'm going to write out that whole thing here so I know exactly what I'm doing. So I'm finding this line in the table. This is my delta y. It's approximately equal to dy dx times delta x. Right? And I might just make a note here. What's my delta x here? How much is my x changing every time as I go from negative 1 to negative 0.5? My delta x is going up by 0.1 each time. That's going to be the same every time. I'm always stepping over the same amount. Okay? So, where are we starting? We're starting at the point negative 1, 1. And if you want to keep track of where you're headed, you know that your x values are going to go from -1 to -0.9 to -0.8 to -0.7 to -0.6, and then finally -0.5. And right here, when we find our y value right here, that's our target number. Okay? It's probably going to involve some calculator work here. Okay, so here, -1, 1. When I find my slope is x plus y. X plus y is 0. So here, delta y is 0 times 0.1, which is 0. So that means my new y value, since I was actually stepping along a little tangent line that has a slope of 0, my new y value, the change in y, is 0. So that means my new y value is still 1. Right? We basically just took a little step along a horizontal tangent line. Okay? Now my new slope here is x plus y, which is 0.1, right, when you add those two together. My new delta y is the slope, dy dx, times the size of my step, which is 0.1, and 0.1 times 0.1 is 0.01. Okay, that's the change in y. So I come back over here and I add it to my y value. So that means now my y value is 1.01. Okay, you with me there? I think I got to get my calculator out now. Now, adding those values together, right, to get my new slope, I add these together. So I have -0.8 plus 1.01. My new slope is now 0.21. And to find how much the y value changes, I multiply together dy dx times step size, delta x, which is 0.1, which gives me 0.021. Right? And then that's delta y, so I come back over here and add it to my y value, and that gives me 1.031. Okay? Now to find my new slope, I just follow the recipe of the differential equation, which tells the slope is x plus y. So now I have -0.7 plus 1.031. That's 0.331. And my new delta y, I multiply dy dx times 0.1, which is 0.033. It would be 0.0331, but I'm going to stop at 3 decimal places here. And that's my change in y value, so I'm going to add that to my y value. So 1.064. Okay, now this will be our last line to get our approximation. I add these two together to get my the slope of my final step, -0.6 plus 1.064. That's 0.464. So you can see that we've been getting steeper as we've been moving to the right. And then I multiply 0.464 times my step size. That gives me 0.046. Right? And then I come back and I add that to my my y value, 1.064 plus 0.046, and I get 1.11. And include that third decimal place. So So my approximation is 1.110. Now let's look back at the picture of this, see if we can make some sense of that. So we started here, right, and we were trying to approximate what is this curve, where is it going to be if we move over and try to follow the guide of these little slopes in our slope field. Well, we took 5 little steps. We took a step here, and we got a little steeper, and a little steeper, and after taking 5 little steps, we ended up, instead of a y-coordinate of 1, we ended up at 1.1. So we didn't end up too much. That kind of looks like, I picked that point because I drew our little sketch through there. And it looks about right. It started to curve upward. If we kept going more and more to the right, it would keep going up and get steeper and steeper. We can talk about, how accurate is this? If you needed it to be really, really accurate, of course you could just take more and more steps, make the step size smaller and smaller, and you could get better and better approximations for what that value is. But typically, at least AP test style, you're going to be asked to do this with 2 steps of equal size. I can't remember off the top of my head ever seeing a problem where you had to do more than 2 steps. Really, in the real world of differential equations and engineering and other folks who use differential equations, this is, I think, clearly the kind of procedure that is much better done by a computer than by a human being like yourself or me. But this is how the process works. When you set up this table, it's really important, even if you're only doing 2 steps, that you're very clear about what all these values are. You need to label these things here, because should you make a mistake somewhere, it needs to be clear that is it only because of one little mistake? Were you actually doing the right things with the number? Were you actually executing Euler's method? So please, especially you lazier folks out there, it's important that you include these values in the table. I would suggest you do the x's, the y's, the dy dx, and then write out what you're doing here, that the change in y, which you're going to add back to your y value to get the new one, is dy dx times delta x. Right? If you needed to go from -1, like more negative, that would mean your delta x would be negative, right? If you got a negative delta y here, that would just mean your y value would get smaller, right? Those are both possible things that can happen. Okay? So, again, what is the use of this? Well, sometimes we run into, we're not going to do a whole lot with this, but should you ever have to use differential equations in the context of studying engineering or whatever, you will likely run into differential equations that are either very difficult to find a solution for or maybe impossible to find a solution for. And this gives us a way of generating a curve, or at least an approximation for what this might look like. Okay? And another way, of course, is just doing the slope field and sketching what it looks like as you go through there. Alrighty, have fun.